Throughout the previous parts of ISO 26262, we've seen how safety requirements are developed and implemented. But engineering does not stop there. Additional analyses are often required to ensure that safety concepts are complete, robust, and free from hidden weaknesses. This is exactly the purpose of ISO 26262, Part 9, ASIL-Oriented and Safety-Oriented Analyses. Rather than introducing another development phase, Part 9 provides analytical methods that support engineering decisions throughout the functional safety lifecycle. In this video, we'll explore the major topics covered in Part 9 and understand why these analyses play such an important role. Before looking at the individual clauses, let's first understand why additional analyses are needed at all. Developing a safety-related system involves many engineering decisions. Even when requirements are complete and designs appear correct, hidden risks may still exist. Components may influence each other unexpectedly. Safety mechanisms may interact. Assumptions may no longer hold. Safety-oriented analyses help engineers identify these situations before products reach customers. They provide additional confidence that the safety concept is complete and sufficiently robust. Now let's examine the structure of Part 9. Part 9 consists of 4 major topics. It begins with requirements decomposition, often associated with ASIL decomposition. Next, it discusses the coexistence of elements with different safety requirements. The third topic focuses on dependent failure analysis. Finally, the standard introduces several safety analyses that help evaluate engineering solutions from different perspectives. Each topic addresses a different aspect of functional safety. Together, they strengthen confidence in the overall system design. Let's begin with requirements decomposition. One of the most widely discussed topics in Part 9 is requirements decomposition. Under appropriate conditions, certain safety requirements may be distributed across multiple architectural elements while maintaining the intended level of safety. This provides additional flexibility during system design. However, decomposition must be performed carefully and according to the requirements of the standard. The detailed rules behind ASIL decomposition deserve an entire dedicated video, so here we'll simply focus on its overall purpose within the safety lifecycle. Another important consideration involves the interaction between different system elements. Modern electronic systems often contain elements with different safety classifications. Some functions may be safety-related, others may not. Part 9 provides guidance for ensuring that these different elements can safely coexist within the same system. The objective is to prevent unwanted interference that could compromise functional safety. This becomes increasingly important as automotive electronics continue to grow in complexity. Even with proper separation between elements, additional risks may still exist. And this leads us to dependent failure analysis. Engineers often assume that different safety mechanisms operate independently. However, this assumption is not always correct. A single event may affect multiple system elements at the same time. Dependent failure analysis helps identify these situations. The objective is to understand whether common causes or hidden dependencies could reduce the effectiveness of the overall safety concept. Because of its practical importance, dependent failure analysis is another topic we'll explore in much greater detail in a dedicated video. The final chapter of Part 9 broadens the perspective even further. The final clause introduces a range of safety analyses that can support engineering activities throughout development. These analyses help engineers evaluate designs from different perspectives. They improve confidence, support decision-making, and help identify potential weaknesses before products are released. The standard intentionally provides flexibility regarding the analytical techniques that may be used. Rather than prescribing a single method, it encourages the selection of approaches that best fit the development context. Now let's see how Part 9 supports the overall ISO 26262 lifecycle. Unlike the development-focused parts of ISO 26262, Part 9 supports multiple phases of the lifecycle. Its analyses can influence concept development, system architecture, hardware design, software implementation, and even later verification activities. Rather than creating new development work products, These analyses strengthen confidence in the work that has already been performed. Before we conclude, let's summarize the key takeaways. ISO 26262. Part 9 introduces a collection of analyses that strengthen functional safety throughout the development lifecycle. These include requirements decomposition, coexistence of elements, dependent failure analysis, and broader safety analyses. Rather than replacing engineering activities, these methods provide additional confidence that safety concepts are complete, robust, and capable of achieving their intended objectives. Many of these topics are extensive enough to deserve dedicated videos, and we'll explore them individually throughout this series. If you want to go beyond this introduction to ISO 26262, we offer comprehensive online training programs on our website. These self-paced courses cover functional safety concepts, ISO 26262 requirements, practical implementation approaches, and real-world engineering applications. The focus is not only on understanding the standard, the focus is on applying it effectively in automotive development projects. You can find the link in the video description and also in the pinned comment below. If you found this video helpful, please consider giving it a like and subscribing to the channel. We regularly publish content on functional safety, ISO 26262, ASPICE, ISO 21434, and other engineering standards. Thank you for watching, and we look forward to seeing you in the next video.